All right, we're back. We're on page 5 of notes 8 of Calc C. We're talking about alternating series. We know an alternating series converges if it alternates, the terms decrease in magnitude, and have a limit of 0. That's the alternating series test. We just figured out that the error involved in a convergent alternating series is just the first term you leave off. It's amazing. All you have to do is know, like, what term did you go up to, and then what's the first term you left off. That's your error. So super easy to use. Now what we want to do is talk about something that's a little bit weirder maybe, but also very awesome. So here is an extremely useful fact about convergence of series. And it's actually another test. And I think it's the last test. So this is it. This is number 11. Series test number 11 is for absolute convergence. So series test 11, absolute convergence. Now this one, just like think it through, and I think it will make sense to you. If the series, the absolute value of a sub n. So look at that. We're taking absolute value. I'm trying to like highlight, but I'm getting killed here. The absolute value of a sub n converges. So instead of letting it alternate, you make everything positive and you add those up. If everything is positive and you add those up and you get a convergent series, then we will say that this series, the original series, converges and is called absolutely convergent. Converges absolutely. Absolutely convergent. Where does the absolute come from? The absolute value bars. Come on, people. But so if we can take the absolute values of the terms and get a convergent series, then the series converges. We don't need to worry about the alternating series test. So this makes it easy because when something isn't like, when it doesn't strictly alternate, like alternating series test doesn't apply, what do? Well, you just hope that it's absolutely convergent and you don't need to worry about it. So this is I don't like 100% understand it because I haven't really looked into it all that much. And that's like a huge failing on my part. Like I should know more about this because I teach it, but I haven't. So if something is absolutely convergent, that's like better than being only converging when you are alternating. So if you only converge when you're alternating, like think of the alternating harmonic series, right? So -1 to the n over n. That converges by alternating series test. 1 over n, which is the absolute value, diverges. So we would say that that series is conditionally convergent. It only converges based on the condition that it alternates, which is fine. But it also means if you look up the Riemann rearrangement theorem, if a series is conditionally convergent, you can apparently rearrange it to sum up to any real number, and I think that's insane. I don't 100% understand it. I don't like 5% understand it. It's not even 100%. Like I'm so far from understanding it, and I've never looked it up. And again, personal failing. What are you going to do? So if we can take the absolute value and it converges, we say it's absolutely convergent and we move on. If we take the absolute value and it doesn't converge, it doesn't mean it doesn't necessarily converge. It could still converge, but it might only converge conditionally, the condition being that it alternates, that it is the series you're dealing with. So let's see if we can do these and make our decisions. So here, first thing I'm going to do is I'm going to look at the sum of the absolute value of cosine of n over n squared, right? And decide what happens there. Well, this actually, the absolute value of cosine of n is less than or equal to 1 for all n over n squared over n squared. So we're going to compare it to this P series. Converges the sum of the absolute value of cosine of n over n squared converges by direct comparison, by dir comp. So that converges. So the absolute values of the terms converge, which means, therefore, the original series, you always got to go back to the original, otherwise what are you answering? Converges absolutely. So we don't have to worry about the fact that sometimes it's positive, sometimes it's negative. It converges absolutely. It doesn't matter. If you made all the terms positive, it would still converge. So like making some of them negative will like make it converge probably faster, but it converges absolutely. Let's do the same thing here. Like this is a really ugly thing to deal with. We're going to look at the sum 1 to infinity of 1 over n squared converges because p equals 2, which is greater than 1. So we can say since 1 over n squared converges, the sum, the original thing we were actually given, don't like writing that, converges absolutely. So when you get into this, converging absolutely versus conditionally versus whatever, it can still diverge, by the way. It's totally possible. You start having to think about all the other series tests. Like we already used direct comparison, p-series, like a lot going on there. Okay, so here, if I look at the absolute value, right, that's just 1 over n. This diverges because it's harmonic. So we know that this series cannot be absolutely convergent, but it can still be convergent. So I'm going to say, but -1 to the n over n alternates, has terms, this is so boring to write, that decrease in magnitude, and the limit as n approaches infinity of 1 over n is 0, therefore converges by alternating series test. So this is conditionally convergent. So I hate that term because the condition is that it is what it is, right? Like if it were another series, it might do something else, but this is the series we have, and it only converges when it alternates, and so it's conditionally convergent. You can also just say it's convergent, but it's only conditionally convergent. So this, if we absolute value this, we get 1 over e to the n, which is convergent geometric, with r equals 1 over e, which is less than 1. Therefore, the given series, I mean, we could actually find the sum of this one, so this one's not. Well, it's absolutely convergent. Converges absolutely, which means you can rearrange the terms and still get the same thing as far as I understand it, which is not very far. All right, let's keep going. This one, so like if you're just doing it in your head, right, take the absolute value, you essentially get 1 over n to the 1/3. That's a divergent p-series. So this can't converge absolutely. But it converges by the alternating series test. So this is conditionally convergent. Now I guess I'll do the work. So, I mean, I guess I need to show 1 over the cube root of n plus 1 diverges by limit comparison to 1 over n to the 1/3, which is p equals 1/3, which is less than 1 for diverges. But then the actual series, I don't want to write this again. Oh, I can borrow it, right? We're doing a copy paste here. Okay, so duplicate. Why'd I duplicate that part? Erase, pick up and move. We're applying the alternating series test, but alternates has terms that decrease in magnitude and the limit. It's like, how much of this would I need to do for it to not be worth it to me to not rewrite this? It would have to be a lot. I think handwriting this is very annoying. More so on the iPad, I think, than on paper. You know, you may have a difference of opinions. So this is conditionally convergent because it didn't converge absolutely, but it did converge by the alternating series test, so it's conditionally convergent. It converges, but only conditionally. This one, I'm going to say that thinking of the graph of arctan, the limit as n approaches infinity of arctan of n is actually equal to pi over 2, right? Arctan, very famous graph. Right. This is at pi over 2. and then that's it, negative pi over 2. So if you're going to infinity, you get pi over 2, not 0, diverges no matter what you do, diverges by nth term test. Okay, so we don't have to do anything more with that, and that is awesome. Okay, we're getting there, we're getting there. This one feels long, it's a lot of writing. Absolute value gives me this, definitely diverges by limit comparison to 1 over, it's basically just 1 over n. 1 over n. And then let us borrow this because it definitely converges by the alternating series test. So I'm gonna try to copy just the part I need, which I didn't really do. Let me move some stuff around. Again, how much would it need to be for me to think this wasn't worth it? So much. Okay, so, well, I could have copied that and just changed whatever. Alternate says da 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 da. This I gotta rewrite. 1 over n plus 3 equals 0. Did I forget that on the last one? Yeah, I did. Go back. What's with all these dots? Ah, they're everywhere. What happened? Sometimes it freaks out. I'm gonna go, there we go. Equals 0. Okay. Conditionally convergent. And then this, if we absolute value it, we get 1 over n to the 1, 0, 0, 1 over 9, 9, 9. This is a p series. Converges. Because p equals 1001 over 9. It's close, but it's bigger than 1. Therefore, thankfully, converges. Absolute convergence is like so much easier to deal with. And 1001 over 999 converges absolutely. Does it converge? Absolutely. Whew. Okay, so you have a little summary down here. If series converges, but not absolutely, then the series is conditionally convergent. And then there's this weird fact, right? So if a series is absolutely convergent, you can rearrange all the terms, you will always get the same sum. If it is conditionally convergent, you can rearrange and get any sum you want. I don't know, Riemann rearrangement theorem. Look it up, and maybe it'll make sense to you. All right, the remainder here is just a summary of things you should have memorized. And so have those things memorized. And we are done with this. And so I'm gonna end this video, and I will see you in the next one where we're gonna talk about something else. So see you there.